the difference between nonlinear and linear analysis. Right? And lastly, the final question is when to use nonlinear analysis. Okay, what is nonlinear analysis? Perhaps we could explain in this way. Linear is the flat earth view, whereas nonlinear is a real world view. Why we come up with this conclusion? We have to look on the assumptions. So these are the assumptions between linear analysis and nonlinear analysis. Linear analysis assumes a constant stiffness, a constant load, and a constant contact. Whereas nonlinear analysis assuming varying stiffness, varying load, and varying contact. Right? So it's very straightforward. Nonlinear is not linear. Right? So let's see what's the fundamental difference. On one side, we have all constant assumptions. Another side, we have all varying assumptions. So this gives a very important implication. Okay, that is, nonlinear analysis always yield a more accurate result than linear analysis most of the time, or every time we should say. Okay, and this is why when we're doing analysis, we are looking on the assumptions whether the problems of that is actually already a nonlinear. Then the linear problem would not give an accurate result because the assumption is already violated. Okay, when to use nonlinear analysis? Right, this question actually related to the past two questions. Right, basically we still go back to the assumptions. Right, when the assumption is violated, we should use nonlinear analysis. But let's have a look. The first of it is constant stiffness versus varying stiffness. Right? The stiffness could be think of a very strong spring is a very high stiffness, or a very weak spring is a low stiffness. Or we can think of material property is something like modulus, elastic modulus or plastic modulus, that sort of things. Right? So what does we mean by constant stiffness and varying stiffness? Or to be precise, when does the stiffness change? Right? There is two factors. First of all is a shape factor. Different shape have different stiffness. Right? The other one is materials factors. Two major factors. Okay. So let's have a look. In the case of big displacement, what is the difference between linear and nonlinear analysis? And then why does that difference exist? Okay, so here we go. We have a metal strip, okay, a very thin strip. This is a hose clamp. What we do, we try to make it in a circle, okay, and then tighten up the screw. At the stage, we will see how the stress is building up during the rolling, right? So this is quite a simple setup. Let's have a look on the boundary condition. For this question, is rather simple. At one of the end, we apply fixed condition, whereas at the other end, we apply a rotation of a radius of 6.25, which is 2 pi, the value of 2 pi, which means this end would actually have a rotation of 360 degrees, a circle, right? And if we put this condition in a linear static study, and in another one identical setups in nonlinear study, what could possibly be the outcomes? Right, let's have a look. Okay, this is the outcome. In linear analysis, you see the things go to the top side, whereas on nonlinear analysis, you see this deform as we expected, right? On a lighter note, these are all true scale, which means that on linear analysis, the deformation scales is 1, right? So the question is, why nonlinear analysis give unrealistic result in large displacement and rotation? Right? The answer is constant stiffness. Why nonlinear analysis give realistic result in large displacement rotation? The answer is varying stiffness. Quite a very straightforward explanation. Okay. What do I mean by constant stiffness? Right, let's have a look. Let's think of this way. When the strip is flattened, we have an original stiffness. Let's say it's K0. Right? What the linear analysis do is we have the load. The rotation is our loading. We'll plug in the loading to get our displacement and then get our stress value, right? So we apply 100 full loading using the original stiffness to give us the final answer. Okay. However, what does we do in nonlinear analysis? What does it mean by varying stiffness? It's the same. Originally, we have stiffness of K0, and we don't apply 100 loading. We apply a certain loading, and then if big rotation or big displacement is encountered, the stiffness will be updated. Let's say until 225 loading is bending like this. Actually, the shape is changed a lot. The stiffness changed a lot, and the stiffness uptake has to be updated. Okay. And then the next loading set, we use the new stiffness to continue find out another result on the next stage. So we have a new displacement, and this stiffness is updated again into K2, and another one, get a new matrix K3, then we go for the final answers. Okay. So this is just more an concept explanation. In the real scheme behind, there could be more steps. But anyways, one important point to note that for the final answer in nonlinear analysis, the stiffness is actually varied during the solving process. Hence, it yields a very realistic results in these problems. So we make a little bit summary. So these problems are large displacement and rotation, right? To capture the realistic result, actually we need the technology of varying stiffness in the solving stage. All right. So different shape, different stiffness. Shape factor is one of the major factors that affecting the stiffness. Another one is material factors. So we have a linear material model for linear analysis, and we have non-linear material models for non-linear analysis. Okay. Let's have a look. This is let's take metal for example. This is a typical material stress strain relationship. Okay. So we have the stress, which is the force per unit area, which is the loading. And we have Young modulus, right? Young modulus is can interpret as the stiffness of the material in the linear zone, right? So this we have you can see on the blue circle. This is a very straight line. This is a constant Young modulus. Right? So and then what does we mean by it is that in here, in the loading stage, the load we have is we can directly interpolate the loads at this stage. Okay? Let's say 80 stress, we use 0.2% elongation. 40 megapascal could yield 0.1% elongation. Okay? But there is a region, a yield region, where we often see in the material sheet, is called a yield. After this yield, there is two phenomena. Okay, the first one is the stress and strain ratio, or should I say Young modulus, is different than in linear zone. Okay, and the second one is that the stress and strain relation could be nonlinear. It's not a straight line anymore. Okay, so this is what we have in nonlinear analysis to predict what happened after the yield point. Okay, and what linear analysis tells us is, will the part yield or not? So usually what we're doing in design is we're trying to design the things before yield. But some of the place might not necessarily have this constraint, because some of the place after yield is still very able to use during the product usage, right? So it's very important to investigate what happened after yield and compare with your linear static result. Right? Before we go to case study, let's go through the next assumption first. The next set of assumption is loadings. There is two components. Whether the magnitude and direction is constant or varying. In other words, during the solving process, is the loading updated? The direction of the loading updated? Is the force actually from small to big, or from small to big to small, or directly from big to small, the profile of the loading? And then we also have the other implication, that is whether it is a time independence or whether it's a time dependence. Or in other words, is it momentum calculated inside F times T? Is the extra loading come inside? And as well as, is there any damping factors, right? This could related to vibration problems. All right, let's have a look. Another case study. I will use daily examples. This is quite simple examples. It's a paperclip. So a paperclip has a very long geometry, which has a shape nonlinearity, as well as it's very thin. So a very light force could make it yield. So let's see what these two assumptions, varying stiffness and varying load, happen in this stage. Right? Let's say we have we're fixing the inner part of the paper clips, and we are applying 1 Newton force at one of the end. Okay. So this, if you run it in a static result, this is what we see. Right? We can see that on the chart there is a red arrow. This is the material yield strength, right? And we have the result. The highest result under this loading is 455 megapascal, right, which is already past away from the U string. Okay. On this point, we can say that the part is U at this circumstance, right? The information after the U will not be accurate unless we perform a nonlinear analysis. If we put the same thing in nonlinear analysis, we can actually make some changes. This is the how we define the force. This is one additional time curve for the force. Right? We can do a little bit further investigation to see more scenario. For example, we can look at the curve and the points. At the original time curve is 0, no loading, means the one end doesn't exist. And then I apply one end, which means it's a fully load, and then I release, unloading. Okay, and this is the result. We can see actually in nonlinear analysis, we are capturing the result at the point of desire. We can do this in one single analysis. For example, I adjust the result to fully load situation. What we see is that you can see the red arrow is higher. Okay, this is the full loading situation, and when we unload it, it comes back to here. All right, it does not go back to origin because it is above the U point. The plastic deformation is captured at this point. Okay, so to compare the difference between linear analysis and non-linear analysis, let's take one example. Let's compare the highest stress we have in the analysis. Right? So for linear analysis, we have 450 megapascal for the maximum stress. For the same material, same loading, same boundary condition, same mesh, a nonlinear analysis gives us around 400 megapascal. Okay? In this case, which is around 15% difference, right? And not just the difference is point of concern, but then we also found that the stress is actually lower. Okay? So actually we can make a more carefully decision to prevent over design, okay, for the problems like this. Okay. Another thing for the material is that just now we have discussed about the metal which have the linear zone. Please be aware that some of the material does not actually have linear elastic zone. Okay, typical examples like plastics or elastomer, right? Or some strange behavior like composite material. So, for example, on the graph here, we have a stress-strain relationship of rubber. You can see the value on the stress ratio actually going very big. This rubber can be stressed to 67%. Okay, more longer than the steel. Okay, so you can see on the curve there is actually no linear zone. Okay, this kind of material in designing an analysis, we will need nonlinear analysis right away. Okay, and the other thing is material property change phenomena. Okay. Yielding material yield is one of the most famous, most popular concept of material property change. Beside of that, actually there is a lot of other phenomena such as strain hardening or creeping. Okay. So this when the material involve material property change, okay, which is a change of stiffness according to the load, it could only be solved in nonlinear analysis. Okay, so on this case study too, we can see that as some examples, actually two assumption coexist, right? So in this case study, we have varying stiffness and varying load, right? What about varying contact? What do you mean by that? This is a more when we involve contact, it usually means assemblies, right? Most of the time. So we can have an imagination that actually contacts, right? One example is that sliding contacts. Okay? There is this constant changing. When there is a lot of changing, usually the stress displacement relation that could be nonlinear, right? For example, like step feet, right? When the plastic is going through the locking piece, actually it deformed quite large, right? And the contacting phase is constantly changing. Something like rubber feet. Rubber is very easily deformed. When we press it in somewhere, the shape of the rubber actually changing very big. Okay. So let's have a look. This case study 3. It is a bending prediction of metal forming, right? So in the left-hand side, we can see this is what we're trying to do. There is a punch that will punch the metal plates into to provide him a bend, right? So as we can see, if we bend like this is a permanent deformance. Okay, so this is varying stiffness, and the load is varying. Right, we come down, come up, and there is contact, right? Varying contacts. So this is the next model. Actually, we in the simulation sites, actually, we only need to prepare 3 things, right? So point of interest here could involve many things, including how can I adjust the spring back effect when I push down and pull up? How do I get exactly, let's say, 45 degree? Or how should I design the fixture? The gap is big or small, right? And how deep I should punch in, right? So this is a lot of interpretation we can do with the result if we can simulate this thing. Okay. So this is some sample setups. Okay. So let's see what does it mean of the time curve over here. You see a very similar thing like the paper clipping. Okay, you see in the front is most likely 0, and we go up to 1 full loading. The 1 in here is a scaling. It's a scale. Let's say we put, for example, 100 Newton. It means 100% loading. Okay, 100% loading, and then we drop back. In here, the loading is our displacement. We use pre-described vertical displacement, which means if I drop down, okay, at this stage, the punch with the no penetration contact actually pushing all the things down, okay, through deflection because the punch is going into the full dip. Okay, so at this point, it's pulling downwards. And then the other stage is fully unload. The punch go back up, okay, and then at this time, the workpiece is already plastically deformed, right? And then we can see what is the result yield in this stage. Okay, so this is the result of it. Okay, so this is a full deflection. T equal to 0.5 second. Okay, this is a time dependence. So actually, the speed of the punch is also have effects on the bending. Okay, so you can see we punch down. This is the full depth. The maximum stress is 97.7. Okay, and then we fully unload. okay, the sheet metal piece spring back up. Okay, at this stage we still have 31.2 megapascal. Okay, there is still stress because that the fixture is still constraining it. They will have a little bit spring back effect. We can continue this study to be further. We can take away the fixture, and then we can see the final displacement is how many, or in other words, the final bending ratio under this operating settings is how many. So we can see this is what we can understand, that is changing of stiffness and changing of loading. But then what does we mean by varying context? Okay, we can look at two places. One is the punching, and one is the contact between the sheet metal piece and the fixture. Let's imagine when this thing punching down, we can see that the face are sliding with each other, right? This is what we mean by varying context. Right. So, varying context is very common in assembly. Assembly, the interaction between parts. Okay, so we observe this kind of context. Okay, it has to be solved in nonlinear analysis. Okay, so we have go through quite a few of things. Perhaps you could look on some examples that related to the problems. Okay, actually, because nonlinear analysis is simulating the real world realistically. Actually, you can say all of the problem is nonlinear. It's just whether it can be regarded as linear or not. So, for example, office chair. Okay, there is a new design that is make people more comfortable, which involve very complex shape. And we sit down, some of the part can experience big displacement. Okay, another very popular example is the step feet. Okay, when we plug something inside, the design of the shape of the step feet is very important, right? Because it related to the stress during the contact, different stress, and then we need to know what is the high stress area and how to reduce it to avoid the U. Okay, for long-term usage, we're going to step feet quite many times. Okay, and for example, the fan guards, there is a lot of bending operation in the manufacturing process. How can we give the proper CAD models to help on the manufacturing side to increase our product quality? Okay, we can investigate the phenomena using nonlinear analysis. And we have a response. Okay, because this involves of time, we can see the response at a certain loadings like vibration, okay, like earthquake, like wind loadings, or transportation. Then of course we have vibration problems. Okay, how big the magnitude it is, and how long it start. How does it start? What is the factors? Okay, so on this stage, what we can see is usually most people believe they should apply a nonlinear solution because of material yielding. But majority of the problem are nonlinear because of large deformation, contact, and time varying load. Okay. So let's make a little bit of summaries. Many applications are nonlinear because of the three assumptions: stiffness, load, and contact. Okay. The other one is about material. Okay. All plastic and elastable should be solved with a nonlinear solutions. Right. So this is a brief introduction of nonlinear analysis. So thank you for joining this section. And now we come into the Q&A section, right? So if you have any question, you can type on using the webinar tool to raise the question. Okay, and then you also can, if you have missed some part of the webinars, you also can request from our marketing staff for the recordings. So is there any questions about nonlinear analysis? Right. So in case there is any questions later on, you can always contact me using email, or my contact number is 0176783988. So thanks for joining this webinar. I hope to see you next time on the next webinar section.